Hey everybody, welcome back to EM378SI Online. We're going to go ahead and just jump right into this problem. This is one of the last bits of our final exam review, going over some lift and drag problems. All right, so we have this 25-ton truck coasting down a steep 7% mountain grade without brakes, as shown in the figure below. The truck's ultimate steady state speed, V, is determined balance by a balance between weight, rolling resistance, and aerodynamic drag. Determine V if rolling resistance for a truck on concrete is 1.2% of the weight of the drag coefficient, and the drag coefficient is based on the frontal area is 0.76. All right. So when something says it's steady state, that means the acceleration is equal to 0. So if I set up our coordinate axis here, and we'll do it this way. Well, no, we won't. X and Y, where X is going along this inclined slope here. We're going to sum forces the X direction. That's going to be 0. So what are the forces that we have going on here? Well, we have the weight. We'll call that W. We also have the drag force. So we'll put that right there. And then also a rolling resistance. I'm just going to call that FR. All right. So, summing things up here, we have W times sine of theta, which is whatever angle is between right perpendicular and the weight that we have, minus our rolling resistance minus drag. And we're going to take that and shuffle some stuff around. So we have W sine theta is equal to our rolling resistance plus our drag. Remember, drag is 1/2 rho velocity squared coefficient times the area. So our weight we know is 25 tons or 50,000 pounds. So we'll plug that in. Sine of theta is, so this angle theta is the same as this angle theta. So sine is 7. Sine is opposite over hypotenuse, so 7 over our hypotenuse. And for rolling resistance, all that is the percent you're given multiplied by the weight. So that's 0.012 multiplied by 50,000. And then we'll plug stuff in for our drag force. So 1/2 the density of air in English units, 0.00238. Some final velocity V that we're solving for is what we're going to plug in instead of that U. We're given drag coefficient 0.76, and the area that we have is this height multiplied by the width that we're given. So that is 10 times 12. All right, and all that's left in this problem is algebra. So subtract stuff over, divide it, square root, and you should get 163 feet per second. That's not really a vehicle unit, velocity unit that we use, so we'll convert that to miles per hour. And that'll give us that our final velocity 111 miles per hour. So this is why it's so important to have those runaway truck ramps on the highway. All right, so that's our first problem. Second problem is a little bit less, well, it's still plug and chug, but there's a little bit more going on. So we have this 0.3 diameter cork ball. Specific gravity is tied to an object at the bottom of the river, shown in the figure below. Estimate the speed of the river current. Neglect the weight of the cable and the drag on it. All right, so the forces that we have acting on our object here, we have drag acting like this, a tension force here, our friend the buoyancy force, and then the weight of the object. So, assuming this is a steady state, we know sum of f of y is 0, and sum of f of x is also 0. So sum f of y, buoyancy minus weight, minus our tension force times sine of 30. For f of x, we have our drag, we'll define our axes real quick. Drag minus t cosine 30. And so we don't really care what the tension is in this problem, and we can calculate buoyancy and weight, and we'll use the drag to calculate the velocity. So because of that, we're just going to solve for things in terms of t, and then plug everything in from there. Or not everything. We're going to solve for drag in terms of t. So drag divided by cosine of 30, that's your tension. So then move that back up into equation 1, and we get that our buoyancy force is equal to the weight plus d over cosine of 30 times sine of 30, which is just our drag force times tangent of 30, but we won't make that difference there. All right, so our buoyancy force, which is gamma times the volume of that's submerged. Our weight, gamma of the cork times volume. And then this mess here. So that is going to be our drag coefficient times the velocity of the river times 1/2 rho times area times tangent of 30. Alrighty. So over here we have 9.80, and the volume of a sphere, 4 pi over 3 times 0.30, 2 squared. So 4 pi over 3 multiplied by the radius squared. And for the for the cork, that's going to be just our specific gravity multiplied by the same thing that we have over here. 4 pi over 3, 0.3 over 2 squared. And then we don't know anything about the drag coefficient, so we'll leave that as it is for now. We also don't know anything about the velocity, but we do know we have 1/2 density of water, 999. Surface area of a sphere, pi over 4 times 0.3 squared, or at least half of a surface area. This is something that would be given to you on an exam. Don't worry about memorizing geometry there. And then our tangent of 30. So let's solve for CD times U squared. So 189 is equal to 35.3 CDU squared. So 5.35 is what's equal to our drag coefficient multiplied by the velocity of our river. So we've run into a situation like this before, right? We have a velocity, but we're looking for some sort of drag coefficient. some sort of coefficient, right? Last time it was a friction coefficient when we were dealing with Reynolds numbers. Now it's a drag coefficient. So we're going to go with a similar process. So if we look at this chart that's in your textbook or would be given to you on an exam, we have the coefficient of drag on a sphere related to our Reynolds number. So let's solve for our Reynolds number in terms of our river velocity here real quick, and then we can do our guess and check method. So U times D over nu times 0.3 over 1.12 times 10 to the negative sixth. So our Reynolds number is 2.68 times 10 to the fifth times our velocity. So so how we're going to go about this is we're going to pick a drag coefficient, guess, and then work from there. So first one that we'll guess CD is 0.5. And if our CD is 0.5, we solve for U up here, and what we get is 3.27. And that makes our, if we check CD of 0.5 and our Reynolds number, what we'll get is something, if we plug our velocity in up here, what we'll get for our Reynolds number is 8.76 times 10 to the fifth. And then we check that with our chart, right? So we'll look down here, check what our CD is. Since I've already done this in prep, I don't really have to look at the chart. And we get a CD of 0.15, which is not the 0.5 we started with, so we have to try something else. So now let's try 0.15, which is what we had earlier. Solve for U up here, 5.97. Plug that in up here, get a Reynolds number of 1.60 times 10 to the sixth. Gets us a CD of 0.20. That's when we look at the Reynolds number that we solved and then check on the chart here. So, problem is 0.200 is not equal to 0.15. And you'll do this until you get an answer that is close enough for your taste. But we'll just go ahead. I know that's going to be 0.19 because I already solved this. So the velocity you get from that, 5.31. The Reynolds number you get from that is 1.42 times 10 to the sixth. The drag coefficient you get from that is 0.19, and that is indeed what you started with. So we get that CD is 0.19 and our U is 5.31 meters per second. Alrighty, so that is that problem. And with the little bit of time that I have left, I just want to say thank you for working with me this semester, not only when we had classes in person, but also through this online transition. I know it's been a little bit weird, but good job persevering, guys. It's been fun working with you. Special shout out to my regulars. You guys know who you are. Anyway, so this week we did a decent amount of exam review, but I am wondering if you want to do one on the weekend. If so, let me know either in the comments or shoot me a message through the SI website. If I decide to do an online session, I'll make an announcement by tomorrow afternoon. Let you know that that's coming. But other than that, hope you guys are doing well in your other classes. Let me know if you have any questions.